Hello everybody, this is Dr. Ross with a reasonably short video on temperature. So I'm going to start sharing my screen so we can get to work making a quick video about temperature. So most of the time in a chemistry class, discussions about how to measure temperature come up, how to convert units from Kelvin to Celsius or Fahrenheit. And we're not going to do that. That's already been done. What we're going to do here is to talk about what temperature is, which is seldom ever discussed. So I prepared some notes and I'm just going to feed you through some ideas on temperature. So there's numerous ways to think about temperature. And one of the first, well, not one of the first ways, but the first way we'll consider is based on kinetic molecular theory. So we comment that there are numerous ways to think about chemistry. Think about temperature. That was an oxymoron. Think about temperature. That's the topic of this video. According to kinetic molecular theory, each degree of freedom has an energy of kT over 2, where K is Boltzmann's constant. So according to kinetic molecular theory, which we'll look at not so much in this video, but we'll look at in subsequent videos. Each degree of freedom has an energy of Boltzmann's constant, lowercase kb, temperature over the number 2, where kb is Boltzmann's constant. Boltzmann's constant. Other than state it, we won't really look at Boltzmann's constant in this video, but it will be coming up in subsequent videos, like in gases, for example. And T is temperature. T is Kelvin temperature. For the most part, if I write capital T, it means Kelvin temperature, not Celsius or Fahrenheit. Okay, so we have something with temperature in, so that's starting to look like something we can solve for. So if every degree of freedom, and a degree of freedom is something that can have a description. So if you've got 2 degrees of freedom, classical degrees of freedom, or if one object has 2 degrees of freedom, not 2 objects. If one object has 2 degrees of freedom, then you need 2 bits of information to describe that object. That's what I mean by degree of freedom. So with 3-dimensional Cartesian coordinates, so thus with 3-dimensional Cartesian coordinates, so what do I mean by 3-dimensional Cartesian coordinates? I mean up, down, in and out, left and right. So just X, Y, and Z axes. So 3 independent planes. And actually I've got, you can put coordinates, but I've actually got coordinate space in my notes. Coordinate space. The kinetic energy. So we said here it's energy. But if we're talking about an object moving, we'll call it the energy of motion or kinetic energy. So we've got kinetic energy Ke is 3 lots of Boltzmann's constant temperature over 2. So every degree of freedom is kBT over 2. We've got 3 degrees of freedom, so we've got 3 lots of kBT over 2. Thus, we can now solve for temperature just by cross-multiplying this expression. Temperature is 2 multiples of kinetic energy over 3 Boltzmann constants. Okay, so we've just cross-multiplied this expression here. So we took this expression here, cross-multiplied. We isolated T, we took the KB downstairs, we took the 3 downstairs, we took the 2 upstairs, etc. Okay, but since we have a bunch of constants here, since the 3 and the 2 and the KB are all constants, so since the 2 divided by 3 KB is a constant, we can get rid of the constant, the equal sign, and add the proportionality sign. So we know the temperature is equal to a constant multiplied by kinetic energy. So we've got our first real glimpse of what temperature is, at least in the kinetic theory point of view. So temperature is something that's proportional to kinetic energy. The symbol means proportional to kinetic energy. So what's kinetic energy? Well, kinetic energy is the motion of molecules. So temperature is proportional to the motion of molecules. Okay, as we'll see here. So we've said that kinetic energy is 3 over 2 kBT, but it's also equal to mv squared over 2, where m is mass, v is velocity, so v squared is velocity squared, and the number 2 is just the number 2. So again, we've still got the relationship temperature is proportional to kinetic energy, but this therefore means the temperature is proportional to m and 2 constants, so just proportional to v squared, which is a bit more information than we had previously. So temperature is proportional to kinetic energy, but specifically it's proportional to the square velocity of molecules. So it's the jiggling around of molecules. So for example, if my fist are 2 molecules and they're jiggling like this, that's a low temperature. But as they start jiggling more and more, that's going to be a higher temperature. So if you cook a piece of chicken, you essentially make the chicken molecules move quicker. If you freeze a piece of chicken, you essentially make the chicken molecules move at a lower velocity. So just a comment on what we've seen so far in words. So we've seen that temperature is proportional to the square velocity of molecular motion. Temperature is proportional to the square velocity. Can't write and speak at the same time. To the square velocity of molecular motion. Because of that, it's now easy to imagine how the melting of ice is accompanied by rising temperature. So again, you imagine you've got water molecules in the solid state, so a piece of ice, for example, and the water molecules are still moving. Ice has some temperature, but they're moving very slowly. And then we start to make the velocity square increase, well, the velocity squared increases, that's proportional to a temperature increase. The temperature increases caused by the velocity squared increase and that leads to the state change and the melting phenomenon we observe from the solid to the liquid phase. So it is now easy to imagine how the melting of ice is accompanied by a rising temperature. Okay, so that's one way of looking at temperature in the bag. So let's go to a second sheet of paper and we'll take a look at an alternative way to look at temperature. So another way to look at temperature is as a balance between, or to consider the balance between temperature and energy. So let's consider the balance between temperature and energy. Okay, an object at a constant temperature must have a balance between its incoming and outgoing energies, right? Otherwise the thing will change. So an object under steady conditions, I don't want to say too much about steady conditions because then we'll have to explain it. I want to keep the explanatory focus on temperature. So an object at a constant temperature must have a balance between its incoming and outgoing energy. Its incoming and outgoing energy. And I think if I can speak with some kind of grammatical awareness, I think there's probably a plural energies. Okay, so for example, so what do I mean? I mean that if I look at the conduction, and I'll explain what these are in a second, conduction energy and the convection energy and the radiation energy of the incoming, so the incoming conduction, the incoming convection, the incoming radiation, should be equal to the conduction plus the convection plus the radiation that's outgoing. You know, if what comes in is the same that goes out, there shouldn't be any change. There's only one of these we're going to focus on, but just real quick, conduction is when two objects are touching each other and there's a transfer of energy along the material. That would be conduction. So for example, if you were to put a piece of metal in a fire, I don't know why you do that, but let's say you did, and you grab a hold of the handle and your hand feels hot, that's because of conduction. Convection is, for example, when you are boiling some water in a pan on a stove, to maybe you want to boil some pasta or something, and the element in the stove is heating the pan is jiggling, and that's causing the water molecules to jiggle on top of it, and then the water right at the top is cold because it's not touching the bottom of the pan, but then the hot jiggling water at the bottom of the pan slowly rises up and causes the water at the top to jiggle and turn. That's convection. So you get convection currents. Radiation, for example, if you've ever had a heat lamp, so you can get radiation or electromagnetic radiation from a heat lamp to keep food warm, or some people have it in their bathrooms. That would be radiation heat. So if all of that incoming is the same as all of that outgoing, there'd be no net deposit of energy, no net accumulation of energy. So there'd just be constant energy. And that would manifest as a constant temperature. Out of all of these types of energy, the one that will get us the most mileage is going to be conduction. So let's focus on conduction real quick. So this is going to be most important for us in chemistry. At least to learn what I'm going to try and tell you. We'll look at radiation later, but at least in terms of what I want to tell you now, it's going to be the most important. Okay, so I'm going to get my black pen back. Okay, so the conduction equation I'll write down as Q by dt, where Q is heat and dt is change in time, is equal to minus a constant. This is not Boltzmann's constant, there's no B here, but it's just another constant. A is area, and then dt by the x. Dx is just space, or the x direction. Let's say it's a one-dimensional space direction. Dt is temperature. So we've got T is temperature, or we can lump it together. Dt by dx is the temperature gradient. Which I'll show you in a second. Dt by dx is the temperature gradient. K is a constant, which is just thermal conductivity. And A is area. Q is heat energy. Okay. And I guess I can put dt is change in time. So what I mean by this temperature gradient is as follows. So let's say this is a high temperature. Let's say this is a low temperature. Right, so that's a gradient, it's a slope. And right now this slope is negative. So I have a negative slope. Right? If you do the rise over run, I'd have a negative slope here as you read left to right. Well, if I put a marble up top here, we know that the marble is going to go in this direction, right? The marble is going to roll down the slope. If the slope was 0, there'd be no rolling of the marble. But if I've got a negative slope, then the marble rolls downhill. So this negative slope is a negative temperature gradient, which is what I have up here. So I've got a so if you look at my equation, my conduction equation, I've got a negative sign associated with a temperature gradient. So that's how you interpret that negative and that temperature gradient. It's a negative slope. And the marble becomes heat. So we consider the marble here as heat. So because of the negative temperature gradient, I get the flux of heat. So heat is a manifestation of the flux of energy between an object that's high temperature and an object that's low temperature in the direction of high to low. So we can write something about that. Let's get back to our black pen. So we can say the negative temperature gradient causes heat to flux from an object at higher temperature toward an object at lower temperature. Okay. So we've talked about flux. Let's see if there's anything else. We talked about the flux of heat. I think that's all I wanted to say there. So we've got this relationship. So initially we saw a relationship between temperature and the jiggling of molecules. Now we're seeing a relationship between temperature as a gradient that can cause energy to change. So there's this, again, there's another type of energy here, heat energy versus molecular motion energy in the first example. So we're starting to see some close relationships between temperature and energy. Relationships, I would say at the first cousin level, not at the immediate sibling level. So one of the biggest mistakes students make is they confuse heat and temperature. Related at the first cousin level, not at the sibling level. Okay, the next way I want you to consider temperature, or at least get a feel for what temperature is, other than its calculation of change, is the scalar field. Actually, I think I commented. Sorry, I actually hadn't finished. I knew something was missing. I just couldn't figure out what it was. I missed some comments here about temperature. Yes. Okay, I wanted to summarize. Sorry, just before we get stuck in scalar fields, I wanted to summarize let's see. Yeah, I wanted to just cap it off by saying that a change in temperature sorry, I'm doing that thing where I'm trying to speak and write at the same time. A change in heat, a change in time, is proportional to minus a change in temperature. Per change in space. So space direction and time, I'm not talking about Einstein's space-time here, just time coordinate and a space coordinate. This is our conduction equation. This is the salient feature with the constants ripped out of our conduction formula, where that change in heat per unit time is just Q by dt. The proportional mops up the K and the A, and then we've got minus the temperature gradient, which is a space direction. Okay, now we can talk about scalar fields. So you can think of temperature as a scalar field. So we can say temperature as a scalar field, which for those that know, it doesn't really matter, but it's a rank 0 tensor. Okay, but scalar field is good for us. So what's a scalar field? A scalar field is, well, first of all, what's a field? Then we'll look at what a scalar field is. So a field is the sum of indivisible pieces of information and each indivisible piece contains one piece of information, the magnitude in some units at that place. So that's a scalar field. So field in general, sum of information, sum of bits. If it's a scalar field or rank 0 tensor field, each bit has one piece of information, in this case the magnitude. So each indivisible piece, indivisible is really hard to say apparently, indivisible piece contains one bit of information, namely the magnitude in some units. At that place. So I'm going to draw an example of what I mean by this field. I'm going to draw a 4x4 grid. So 4x4 grid, let's say you call these indivisible pieces A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. All right. So you've got this two-dimensional grid called our scalar field. So we're saying that our scalar field is the sum, because we have to, if it's got all these pieces, to talk about the whole collective, we have to sum over the pieces. So sum every square, let's call it n, and I could be, so let's say here n is a square, and then the symbol I could be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So any one of those squares I'm going to generically call I. And then if I sum over all I, then anything with the symbol I, I'm going to add together. So that would add everything in that field, where I equals A, B, C, all the way to P. We've said already that temperature can be considered this way. So if you take the room in front of you, split it up into a grid like this, And every spot in the room, there's a temperature that has a value. Temperature is a scalar field. Doesn't matter what the unit is, it's always a scalar field. Sorry, there's my alarm, which I forgot to turn off. Scalar field. So temperature is a scalar field. For example, just do a 2x2 grid here. This grid could be 5 degrees. This grid could be 6 degrees. This grid could be 10 degrees. This grid could be 5 degrees again, etc. So there's only one piece of information. So we can consider, so that's 3 different ways we've seen so far for temperature: a scalar field proportional to the velocity squared jiggling of molecules, and then linked in a way the balance between energy and temperature. We saw that temperature gradient and energy can flux down gradients or not flux at all if there's no gradient. Okay. Yeah, so a couple more ways to look at temperature. Okay, so actually, do I want to show you that way now? Yeah, let's go immediately to this. So let's look at temperature from a thermodynamic point of view. Temperature from a thermodynamics point of view. We look at thermodynamics a bit later in our course. For now, thermodynamics, dynamics just means change. Thermo means heat, which manifests in a temperature change. So we're looking at temperature from the viewpoint of heat and temperature changing. So it's kind of a definition already built in. Thermodynamics considers temperature. Now temperature, now I'm going to put an equation up here that might make some people stop watching the video. But I promise, as much as I can, if you don't stop watching the video, it will help you if you just stick with it. So that's just a warning. Temperature is equal to a fraction, the partial derivative of total internal energy over the partial derivative of something called entropy, which we'll say a couple of words about, at fixed or constant volume and fixed or constant number of molecules. So here we've got U is total internal energy. We'll actually see U a bit later on in our course when we look at the first law of thermodynamics. We'll see U, but we don't have to see it right now. S is something called entropy. Now, we don't have to study entropy in this course, but I'm going to mention a few words because it comes up in several places, but the label entropy is avoided typically by people, but the concept that's being used is really entropy. So we will get back to entropy in a second, just to give you a flavor for what it is. These are partial derivatives. Partial derivatives. Why partial? Partial means there's more parts that are changing. So a derivative is just something that changes. If you have a partial derivative, it's because it's part of a collection of things that are changing. That's all. Okay. And just want to put here, parentheses Vn. This just means a constant volume and number of molecules. Okay, so there's some funny math symbols here that you may or may not be comfortable with, but let's look at what we do have. What we can see right now, if this is true, temperature is equal to some ratio, then temperature must be an intensive property. Temperature is an intensive property. So remember we said intensive properties are properties that are constant. They have a numerator and a denominator, both of which have units. So it's important, realizing the temperature is intensive is not, I don't think it's that intuitive, but once you know it's an intensive property, I think it really helps. And because intensive property is very valuable, temperature, measuring the temperature of something, you've learned a lot about it. So all I want you to know for now, if you're looking at this thinking, do I have to learn partial derivatives? The answer is no. I want you to look at that and know that, okay, temperature is an intensive property. Again, we can see temperature is proportional to an energy. So we've seen here, if you look at this expression and then break it down, it basically says that temperature is proportional to a type of energy. So we've seen that before. This is not kinetic energy, but it's proportional to kinetic energy. So in total internal energy is proportional to kinetic energy. We'll see in a future video, but we've also seen in this video the temperature is proportional to kinetic energy. So that's nothing new, but what on earth is this thing called entropy? So that's where I want to spend a few minutes just discussing. And this will conclude the video. Once I've explained a little bit about what entropy is, you'll be glad to know this will wrap up this video. So I want to spend some time just looking real quick what entropy is. And then we'll go back and convince ourselves that we've lifted as much information as we can out of temperature. Okay. So preface to entropy. So we're not going to look at entropy proper, but I just need to, I've mentioned it, I need to give you a feel for what entropy is. And it's to do with, it's heavily linked with the arrow of time. So let's have a quick look. So the laws of physics don't have a preferred direction for small samples. Laws of physics don't have a preferred direction period. I mean, the laws of physics don't have a preferred direction. And it's easy to see this for small samples. And this is what I mean. So let's say you have a molecule here, I've shaded it in black, and this molecule is on a collision course with a molecule that I haven't shaded at all. So let's say this molecule is moving in that direction, and this molecule is on a collision course in that direction. And they collide in the middle, and then the white sphere bounces off, and the black sphere bounces off as well. Okay, so imagine, again, coming in from the left, you've got the white and the black sphere. They come in, bounce, and then leave each other like that. So small sample, I've only got 2 objects to keep track of. So we've got in the plus time direction, if I were to look at this backwards, if I recorded it, ran the tape backwards, this would be the minus time. And clearly there's a plane of symmetry here. So if I chop this event in the middle, let's say this is a mirror, then this looks the same and this looks the same, right? That's what I mean by there's no apparent preferred direction. So clearly, if you view this collision in the plus time and the minus time directions, this collision in the plus time direction and minus time direction, it looks the same. It looks the same, and in fact, it doesn't just look the same, it's actually indistinguishable. Distinguishable. Okay. So hopefully everyone's on board with that, not a hard sell. Now let's make the sample a bit bigger and we lose that indistinguishability. So however, a larger system would be distinguishable in both directions. So a larger system, which just means we've got more spheres, would be distinguishable in the plus time and minus time directions. Plus, not only is it distinguishable, but it's not reproducible. So you do it once, somebody says do it again, you can't, you're going to get a different outcome. So that's even worse, right? It's irreproducible. Which means unlikely, not impossibly, but unlikely to be duplicated. So for example, think of playing a game of pool and you break off, the white ball hits the triangle, and then do it again and see if you can reproduce exactly the same break. It's very unlikely you're going to do it. So imagine a black sphere comes in on that trajectory and you've got a bunch of spheres it's going to hit. Let's say a black sphere here, a black sphere here. Let's say a white sphere here, another white sphere here, and a black sphere here. Let's say this black sphere goes off in that direction. This white sphere goes off in that direction. This black sphere goes off in that direction. This white sphere, this direction, and this black sphere in this direction. Well, first of all, we've lost our symmetry, right? This is not the same to the left of that line, and this is not the same to the right of that line. So we've totally lost it's distinguishable now, we've lost the symmetry, plus there's no way we could reproduce that in a likely scenario. So plus and minus time are clearly different, but now they're irreproducible as well. Okay, so what's this got to do with entropy? Well, let's have a look. So thus, there seems to be an order to change that follows time. There appears to be an order to change that follows time. So what do I mean by there's an order to change? I mean that as time, what you don't realize here is time seems to have nothing to do with the order of events. Clearly here in this larger sample, time has a role to play, or not time absolutely, but the arrow of time to the order of events. So I could clearly now, just from experience, tell you which is the forward direction and the reverse direction, just based on my awareness of likelihoods. So there appears to be an order to change that follows time. And this is how we can tell if we're watching reality in the plus or minus time direction. Reality in the plus time or minus time direction. So when you see somebody jump into a pool and the water splash everywhere, and then it's recorded, and then you reverse the tape, you see water splashing and then somebody jump out of a pool, your brain knows that that's backwards in time, because you're looking at this notion of the irreversibility, the statistical unlikelihood of certain events happening in the positive time direction. Okay. So to address this order of change and direction of time. So to address this, and why do we have to address this, which is not a fundamental feature in physics equations? It's actually still not, I almost said it's not a fundamental concept in physics. It's still, to my knowledge, it's undecided. People debate either way, but certainly not in the mathematical equations. So it's not fundamental in the mathematical equations. So to account for it, despite it not being in the fundamental equations, entropy was invented. By people like Josiah Willard Gibbs and Ludwig Boltzmann. So anyway, so that's probably enough to say about that. Again, we don't really want to get into entropy proper here, but just to give you a feel for what it is. So entropy is a way to bucket. It's like a big box, and you shove into that box understanding about why events in the plus time direction and the minus time direction can be different. That's entropy. So the whole point of telling you all that was to go back to the temperature, because this is a temperature video, right? So temperature is proportional. Let's write that again right at the end. So just to remind everyone. So temperature, we said, was the partial of total internal energy over the partial of entropy. Oops. a constant volume and constant number. We've said that temperature is proportional to total internal energy, which is proportional to kinetic energy, which is proportional to the square velocity of molecules. We can also see now that it's proportional to 1 over entropy. And what else did we see? We saw the temperature gradient, right? How would we feature that in real quick? We could say, yeah, okay, we could say that. Well, that's just energy, right? Heat is energy, so we've already said it's proportional to energy. So that'll probably do us. Yeah, we've got energy in there. So temperature is proportional to energy, different types of energy, different manifestations of energy, molecular motion, entropy, or increased degrees of freedom, degrees of freedom. Okay, so have a look at this video, pause it, rewind it, what have you, but hopefully this will complement what you've seen in your textbooks about how do I measure temperature. This will give you a feel, a non-exhaustive feel, but just some introductory thoughts about what temperature really is. And I've stuck with ways that will be helpful to us in the rest of the class.